Picture one demanding game frame arriving at the processor. Transistors switch, useful work gets done, and some electrical energy becomes heat. Our story follows that heat all the way out of the computer. That journey is the real meaning of PC cooling. A cooler does not destroy heat, and it cannot make room temperature disappear. It moves energy from a small, hot piece of silicon into the room around the machine. The first handoff is microscopic. Heat must travel from the chip package into a cooler cold plate. The two surfaces may look smooth, but tiny gaps remain. Thermal paste fills those gaps. Paste is not magic and more is not automatically better. Contact, suitable mounting pressure, correct hardware, and a reasonable application all influence this thermal interface. If a newly installed cooler behaves badly, verify the mount before buying another product. From the cold plate, air coolers and liquid coolers take different routes toward the same destination. An air cooler uses heat pipes to carry energy into a large fin stack. A fan moves room air through those fins, and the warmed air leaves the case. A liquid loop uses a pump to move coolant from the cold plate to a radiator. The radiator still needs fins and airflow. Liquid cooling relocates the heat, it does not remove the need for ventilation. Each route has practical trade-offs. A large tower cooler needs socket support, memory clearance, case height, and a sensible airflow path. A liquid cooler adds radiator clearance, tubing position, a pump, and more possible failure points. Pump orientation and radiator placement matter, as do maintenance and the exact manufacturer instructions. Choose a system you can install, inspect, and live with, not the one that simply looks most dramatic. Now the heat reaches the case. Intake fans bring cooler air in. Exhaust fans help warmed air leave. More fans are not automatically better if they fight each other, recirculate air, or run so fast that the computer becomes unpleasant. A useful fan curve is quiet during light work and responds smoothly under sustained load. Ambient room temperature matters because every cooler begins with the air available to it. This is why isolated temperature screenshots are weak evidence. Compare the same hardware, room conditions, workload, duration, settings, and measurement method. Watch temperature together with clock speed, power, noise, and completed performance. A processor running warm while holding its intended clocks may be behaving normally. A machine that gets hotter, loses clocks, and slows during a repeatable task may have a cooling limit worth investigating. Before tuning, confirm socket compatibility, cooler rating, physical fit, fan direction, pump connection, and clean vents. Establish a repeatable baseline. Change one variable, such as a fan curve or mounting correction, then run the same test again. Do not compare unrelated workloads or force every fan to maximum all day. The thermal journey ends in the room: silicon, interface, cooler, fins or radiator, case airflow, then ambient air. Follow that chain and cooling becomes understandable. Measure the full behavior, fix the weak handoff, and aim for stable performance at noise you can accept. That is cooling that makes sense.